Okay, so we're going to do our last of our distributions today, which not today in the continuous section, which is the gamma distribution, and then next time we're going to something new. So we've got a random variable y, and it's got a gamma distribution if it has the following function. So here's our probability density function. So there's our probability density. It's defined for y greater than 0, and it's got two parameters now, alpha and lambda. Now, if you look carefully, you should get a little bit of deja vu at this point. Notice this bit here. That is very similar, in fact identical to the exponential. And in fact, one of the ways you can derive the gamma distribution is, let's assume we had a load of exponentials, all the same rate, and we added them together. In fact, we added together alpha of them, we would have a gamma distribution. And there's a specific name for the case where your alpha, because if you notice at the moment, this alpha can just take any value. But if you have that your alpha is a natural number, sort of 1, 2, 3, 4, 5, in some texts you'll see that called the Erlang. So let's just write that down, the Erlang distribution. Basically, the Erlang distribution is a gamma distribution where alpha is a natural number. Now, the second bit we've got here in our distribution, that all looks fine, but we've got something funky going on underneath. That is a gamma function, hence the name gamma distribution. So what is the gamma function? Well, the gamma function is a function that takes a single number and basically it calculates this integral. Okay, so let's look at this in more detail. So we've got some properties. First of all, the gamma of alpha plus 1 equals alpha gamma of alpha. So we've got this nice recursive relationship. The gamma of 1 equals 1. And if alpha is an integer, n, then the gamma of n is equal to n minus 1 factorial. Well, what we're going to do is we're going to actually have a look at the sort of the general properties of these. So let's go and... So we're going to consider the gamma of alpha, which equals 0 to infinity y to the alpha minus 1 e to the minus y dy. Right, I'm going to go integrating this. Now, to do this, we're going to do integration by parts. So let's remind ourselves what that is. Well, first of all, let's look at differentiation. Imagine I had two functions f and g and I differentiated with them. Well, by the product rule, that would be f dash of g plus f g dash. So that's the product rule. Well, we could rearrange that and you could say that f dash of g equals fg dash, minus fg dash. And if I integrate both sides, I get the integral of f dash g equals the integral of fg dash minus the integral of fg dash. And if I take something that's differentiated and integrated, I get the same thing. So I get f of g minus integral of fg dash. So the idea is, I want to integrate something. And what I'm going to do is, I notice it's made as the product of two parts. I'm going to take one part, the f part, and I'm going to integrate it, and the g part and differentiate it, and then substitute that into here. Okay? It's more complicated than it seems. So let's set it up for our case. So we're going to set f dash is equal to e to the minus y, which implies by integration that f equals minus e to the minus y. I'm going to set g equals y alpha minus 1. So by differentiation, I get g dash equals alpha minus 1 to the y alpha minus 2. So now if I want to integrate, I'm just going to substitute in to this. So I've got f, which is minus e to the minus y. I've got my g, which is y alpha minus 1. And I want to do that from 0 to, I just substitute in 0 to infinity. Then I've got to do minus the integral from 0 to infinity. I now need to do f, which is minus e, well I could change that to a plus, e to the minus y. And then I need g dash, which is alpha to the minus 1, y to the alpha minus 2 dy. Okay, so there's just a recap of our integration by parts. Well, let's look at the first one. I've got minus e to the minus, we substitute infinity, so e to the minus infinity, and I've got infinity to the alpha minus 1. Well, which one wins? Do we get the sort of the e to the minus infinity going to 0 or infinity to a power beating? Well, e to the minus infinity gets there quicker, so this actually, the first term is 0. When I put in 0, I get e to the minus 0, which is 1. And then I get 0 to the alpha, which is 0. So the whole thing is 0. So that first term is 0 minus 0, which equals 0. Plus, what have we got in that second term? I've got 0, infinity. I'm just going to rearrange it. I'm going to go, this is alpha minus 1 to the y alpha minus 2, e to the minus y dy. And what is that? That, if you look at it carefully, if I bring an alpha minus 1 out to the front, is gamma to the alpha minus 1. So what have we shown here? Well, we started with gamma alpha, and we did an integration by parts, and we found that we now get alpha minus 1, gamma alpha minus 1. We've built that recursive relationship. We saw it in the first slide before, in terms of alpha plus 1, but I thought this would be just a little bit nicer. You could do an integration by parts to show that alpha of 1 equals 1. I'll let you do that in your own time. You just need to do integration by parts once and it drops out quite nicely. So the mean and the variance of gamma distribution, well, the expected value of y equals alpha over lambda, which again sort of makes sense. If we had this idea that you could get a gamma by adding together alpha exponentials all with the same rate lambda, then you know the expected value of y for an exponential would be 1 over lambda. So if we add a load of them together, we'd get alpha over lambda. The variance of y equals alpha over lambda squared. And the moment generated function is 1 over 1 minus t over lambda to the alpha. Which again, if you look carefully, is like an exponential, but we've just multiplied the bottom by itself, alpha times. There's a special case of the gamma that you may have heard of before. So imagine we've got a gamma random variable and it has a parameter alpha equals, now that looks like a V, it's not. That's the Greek letter nu. So it looks like a V, but it's nu, so nu over 2, and we let lambda equal half. Then that PDF there is actually a chi-squared distribution, and it's a chi-squared distribution with nu degrees of freedom. We'll come back to the chi-squared in a short while, because you can also show that the chi-squared distribution 1 degree of freedom you get by taking a standard normal and squaring it. And to actually show that, we'll need to start looking at how we get distributions for transformations of random variables. Cool, so that's the end of week 5. Next week we're going to do the Poisson process. So not the Poisson distribution, the Poisson process. And we're going to start looking at transformations of random variables. See you next week.